Hello YouTubers. I'm here to actually to help my class a little bit. We're reviewing for an exam and I thought maybe you could benefit from it also. What we're going to do, we're going to be solving parallel problems using a calculator. Now I know most of you like to do all your complicated problems longhand, but in this case what we want to do today is utilize the calculator so that we can solve these problems with a fair degree of speed. Now, let's look at this parallel problem. We have 3.3 k ohms, and the symbol here, for those who don't know, means in parallel. So we have 3.3 k ohms in parallel with 20 ohms. Now, we could solve that problem using longhand. And what we could do, we could use this formula. We could use several formulas, as a matter of fact. We could say that RT equals the product over the sum, which is R1, R2, R1 plus R2. But we sort of decided in my class that probably using the calculator, it's just as fast to not have to remember all these formulas. So the one we use is the product over the sum. No, I'm sorry, the one we use is the reciprocal formula, which is RT equals 1 over R1 plus 1 over R2 out to 1 over N, which means any number. Okay, with that said, let's solve this problem. I'm going to use the reciprocal formula. And in this case, it equals, and we'll use a calculator in order to solve it. First, this is a TI-30XA calculator. It's a scientific calculator. Very inexpensive, $8.95. Well worth your money. What I particularly like about this calculator for my entire course, both AC and DC theory, and also we can do digital with it, is the fact that it's simple and it's straightforward. And if you start on this particular calculator, then what you're going to do, you're going to be able to use this for several courses. So the first thing we do, of course, is turn the calculator on. You can see I previously worked a problem, so I want to clear that. Now, this is showing me that I'm at 2 decimal places accuracy, and I'm in scientific notation. I want to show you how to get into scientific notation for those who don't know how. So I turn the calculator off, I turn the calculator on, and I hit the second function. Now, the keys are printed with certain numbers and certain things like the cosine or the sine. Now, in order to get to the other functions that are printed on the body, for example, here it says SCI underneath the 5, what we have to do is hit second, and we hit scientific notation. Whoops, let me clear that. We hit second, and we go into scientific notation. Now notice here that we've done that. We've established a number and exponents for the powers of 10. Now we want to set up the accuracy for my particular class, two decimal point accuracy. So I hit second, and then I hit fix down here, which is underneath the period, and for 2 place accuracy I hit 2. Now notice what we have now. We have 0.00 and exponent of 0, 0. What that's telling me that the calculator is now set up in scientific notation with a 2 decimal point accuracy. Now let's look at the problem at hand. We have a 3.3 k ohm resistor in parallel with a 20 ohm resistor. In order to work this problem, the first thing I do, I put in the 3.3. Now here comes the part that some people get confused on. I want to put in the exponent. Instead of k, I want 10 to the third. So in order to put 10 to the third up in this window, I hit double E, and then I hit a 3. It's simple as that. So now I have 3.3 times 10 to the third, which is 3.3 k ohm. K ohm. In the metric system, K stands for 1,000. So that's how much? 3,300 ohms. Okay, now the next thing we do, we're going to follow the formula of the reciprocal here. We put in r here at r1. Now we need to take the reciprocal of that, and we have a function key here that is reciprocal, so we hit that. Okay, now we want a plus because we're going to the next part of this problem, so we hit plus. And now we have 20 is all we have. We don't have any k ohms there, it's just 20. But we still have to put in the reciprocal because it's 1 over 20. So we've got the 20 in, now we hit the reciprocal. And then we hit equal. And then we hit the reciprocal because the whole thing is going into 1. Okay, the answer is 1.99, I'll write that down, 1.99 times 10 to the first power. Now, the answer is correct, but it's not in our standard form. These are resistors, so in our standard form, what we want to do, we want to write it this way. Okay, we have 1.99, and we want to get rid of the 1 here. We want to get rid of the power of 10. We just want it in the units. So what we do, this 1 here will increase the amount of resistance that we have on 1.99. And what this is called a caret. Use a caret instead of a decimal to indicate that you've changed where your decimal point is. So now what we have there is 19.9 ohms. So it follows the rule that once you put resistors in parallel, this is important, once you put resistors in parallel, then the sum of those is going to equal what? It's going to be less than the smallest resistor in parallel. Now let's do another one. This is a little different problem. Notice there's something unique about this problem. Let me see if you're looking at that. Let me move this over a little bit. Up is down and down is up here. It's difficult on this old Elmo. Okay, so what we're going to do now is we're going to solve for this one. Now, we could use the reciprocal formula. We could use the same formula, and I would advise most of the time you do. But on the other hand, I want you to be able to work it both ways and realize that you don't have to use a reciprocal. Now, this is only the case when the numerical values are the same. This is 5,000, this is 5,000, this is 5,000. That's what 5K is, 5,000. So what we do, we look at this and we're going to use a little different formula. We're going to say that RT is equal to what? We pick out one of the resistors, they're all the same, so any one doesn't matter which one you use. So that's 5K divided by the number of resistors, that's the counted number, 1, 2, 3. So we have 3 resistors here. Now we clear our calculator because we're on a different problem. We clear our calculator and we're going to put this problem in. We're going to say 5 double E 3. Notice that's what I have in the window here, 5 double E 3 divided by 3 equals 1.67 times 10 to the third. Now again, this answer is an answer. It could be, as long as you put that in ohms, it would be understood by people who understand electronics. It would be understood, that's the answer, could be 1.67 times 10 to the third. But that's not acceptable at your level in this class. So what we're going to do, we're going to convert that. We're going to convert that into just straight ohms. We're going to get rid of this 10 to the third. And here's the way we do that. We write down to 1.67. And we're going to have to move this decimal point 3 places to the right. Now, we're not going into negative numbers right now where that decimal up there will be a negative. We can talk about that another time. But for now, we're going to always be going to the right in these problems until I tell you different. Okay, So we need to move that decimal point 3 places to the right. There's 1, 2, 3. Now remember, the caret just indicates the new place for the decimal. So what does that equal? That equals 1670. 1,670 ohms. 1,670 ohms. Now, if that's what you have on your paper, I'll accept that as correct. But more preferable would be this. What? 1.67 k ohms. Now, I did that for illustration. By inspection, you should be able to look at this 1.67 and tell that that third means k, the 10 to the third. So you wouldn't have to go through this step here, would you? This would be a correct step, just to write down 1.67 k, because it's 3 there, isn't it? Okay, now let's do another problem. I'm going to clear my calculator. I'm going to look at the next problem, and this is what it is. Okay, problem number 3. We have a 5K ohm resistor. I don't know, can you see that? I don't know why the camera's tilted, but maybe I could correct that a little bit. Well, maybe not. Maybe not. It's probably more like it. Maybe I can. Let's try it for heck of it. Let's try to adjust that camera. Okay. That's about the best I can do right now. So I'm doing number 3 on the list that I gave my students last week. And it's 5K in parallel with 3.9K in parallel with 50K ohms. And all of these are in ohms, by the way. I should have written that down on some of the other ones, but realize these are all K ohms, or ohms, straight ohms here. Now let's put this so you can read that. So what we have a 5K ohm resistor, and these lines, these two vertical lines mean parallel, with a 3.9K ohm resistor and a 50K ohm resistor. Now let's use the reciprocal formula. I'm not going to write this every time. I just want you to know what we're doing. After you get done doing this, you will be able to just to put it into your calculator. Now, if you want me to know on an exam that you know what you're talking about and didn't come up with some answer, some stray answer, then you could go ahead and write the formula, which I sort of advise. Now, that is if you have time. So RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Okay, now let's rewrite that. Let's put in some numbers. So RT, let's see, you can still see that, I hope. Maybe I can move it up. There we go. So RT equals 1 over 5K. This is all over 1, by the way. 1 over 5K plus 1 over 3.9K plus 50K. Okay. 1 over 50K. Now I know that I've told all of you to use a pencil when you're doing these problems so you can erase. Unfortunately, you wouldn't be able to see this if I use my pencil. So I'm going to have some hand scratches here. So let's go ahead and work that problem now. Okay, I want to move my calculator over so you can see it. And I might even zoom in on it. I think I might. I think I'll zoom in a little bit the best I can. Okay, let's see how we can do. That's a little better. Okay, now let's do this. Let's look at the calculator and see what we're going to put in. We're going to put in 1 over 5K, we're going to put in 1 over 3.9K, and 1 over 50K. We clear the calculator. We see we're still in scientific notation with a 2 decimal point accuracy. So the first thing I do, I put in a 5. We're doing this right here. I put in a 5, doubly 3. Now, I've got to take the reciprocal of that. So I take the reciprocal, and then I say plus, this plus sign right here, plus what? 3.9 double E3, that's 3.9K. And again, I've got to take the reciprocal, plus, what now? 50 double E3 reciprocal equals. Now notice up here that we have a negative number. That tells you you're not done yet. We're normally not going to have a negative resistor. I'll go into that another time, but normally in this class you will not see a negative in the powers of 10. As far as the resistors go, you will in current, but not as far as the resistors. So if you get a negative in resistors, just know that you're not quite done. And here's why you're not done. This whole thing down here is going to go into 1. It's going to take the reciprocal of that. So I hit the reciprocal again, and the answer is, let me put it in with a pen. Hope I don't have to do it again. 2.10. Now notice I have 2.10, and I have a 3 up here. Now that we demonstrated what that is, we can just go ahead and write that as K, because the 3 in the powers of 10 is going to be K, and we're doing resistors, so the value is going to be in ohms. Now a good way to check yourself, of course, is to go through this and check yourself. I'm going to go up here to the top. I'm going to clear the calculator, and let's see if we can get that in there reasonably rapid. So what I do, I push in a 5, and I put in double E for 3, and then I take a reciprocal, right? And then I hit plus 3.9 double E3 reciprocal, 50 double E3 reciprocal equals. Now we see that we have that negative up there again. And the reason is we need to take a reciprocal again, because this whole thing here is going into 1. So I take the reciprocal, and I get 4.55K. Okay. Does that make sense to you? No, it doesn't, does it? We came out with a different answer, didn't we? Did I do that on purpose? I'm going to write that down just to sort of keep it stored in my mind. 4.55K. Now, let's clear that. Let's do it again. Okay. We have a 5K, 3.9K, and a 50K. So here we go. I put in a 5, double E3, reciprocal, 3.9 double E3 reciprocal, 50 double E3 reciprocal equals. Now, let's go over that one more time. One more time. See how this can be? You've got to pay attention to what you're doing. You put in a 5. So don't get carried away and try to do these too fast. You put in a 5, a double E, and then 3, reciprocal plus 3.9 double E3 reciprocal plus 50 double E3 reciprocal equals, and reciprocal again. Lo and behold, we were right the first time. 2.10 times 10 to the third. So it's 2.1 K ohms. 2.1 K ohms. So now we've solved that problem. Now that's what I would advise you to do. I would advise you to keep poking until you can get at least 2 answers that are the same. Now there is a possibility, an outside possibility, that you could actually be making the same mistake twice. But I'm sure you're going to let me know if I was right. A lot of times what I do, I'll go ahead and circle the answer, and or put a square around it, or a rectangle. And let's see, the one here. Here's the answer to that one. Okay, are we ready to go to the other one? And my screen just blanked out. Let's see what happened here. I think I timed out on my computer. No, it's going to be a hassle getting that back. Okay. I think we can go ahead, though. I don't think I need to get this back right this time, but it would be nice to see what's actually on the screen. Okay, I hope I don't go through all these and find out I have to do it again. But we're working fine. We're doing fine here. So, number 4 is 60K. 1, 2, 3, 4, 5. 6 60K ohm resistors. So I have a 60K. Let me count that again. 1, 2, 3, 4, 5. I have 5 60K ohm resistors. 60K in parallel with 60K, in parallel with 60K, in parallel with 60K. 1, 2, 3, 4, and 5. 2, 4, 5. Okay, 60K. It's all right to think out loud. Nothing wrong with that at all. Now, we're not going to use a reciprocal formula, because, and we could double check ourselves with that, but we might as well use this formula that we used over here. Anytime you have the same size resistors, and notice these are the same size resistors, so what you do, you say that RT equals the size of one of these resistors, it's 60K, divided by the number of resistors, 1, 2, 3, 4, 5. Okay, and that equals, we'll go ahead and plug that into our calculator. Let's see, can you see it yet? Not quite, but it's close enough. Okay, I'm going to clear the last problem, and I have 60K divided by 5. 60, that's 60, E3 divided by 5. I bet it's going to be 12. What do you think? 12K? But we want to work on the calculator. Now notice my answer is this. Let's make sure you can see it. It's 1.20 times 10 to the 4th. Now remember what we're doing? Even though this is a correct answer, it's not a correct answer for our test purposes. We want this resistance to be in ohms, and we don't want it to be with a power of 10. What we normally want is either just ohms or k ohms or meg ohms. Okay, so here's what we're doing. Let's look at this. We have 1.20 times 10 to the 4th. So I'm going to have to move that decimal point 4 places, aren't I? 4 places. 1, 2, 3, 4. So that turns out that's a 12,000 ohm resistor. But remember what we discussed before? We can change this where we have 1.20 times 10 to the 4th, and we can change this number here, and we can take 1 away from here, and then it's going to be 10 to the 3rd. 10 to the 3rd is a good number for us, isn't it? Because 10 to the 3rd is K. So to make this 10 to the 3rd, I need to move this decimal place to the right. So now I have 12.0, what? 12.0 K ohms. I hope you're getting that, and if you're not, you need to go over that a couple of times. That's a fairly important point. The truth is, if you get this answer here, 1.20 times 10 to the 4th, I will know you know what you're doing, so I'll give you partial credit. But why not get full credit and put down 12.0 K ohms? Okay, there's that one. Now, are we ready to work another one? Let's do number 5. Number 5. Okay, number 5 says 8.2 K ohms in parallel with 100 K ohms. Okay, can you tell me what's the greatest size this resistor can be that we're going to figure out the total of these two? It's actually going to be less than 8.2 k ohms, isn't it? Because in a parallel circuit, test question, in a parallel circuit, the combination of the resistors in parallel are going to be less than the smallest resistor. Now, let's do that on the calculator. Let's move it over here so we can see it. Okay, I think you can see it now. Not quite. Okay, I can see it now. I need this screen in front of me because I have to turn around in order to do this. My table's not big enough, but I'll get a bigger one. Okay, so let's start over. We clear our calculator. I want you to note that we're still in scientific notation, and we're at 2 decimal points. So what we need to do now, we're going to put in 8.2k first. So it's 8.2 double E for the K, double E 3, reciprocal, what? Reciprocal plus 100k, 100, double E 3, reciprocal, no plus this time, but equals. Okay, now we need to see that's negative again, so we want to take the reciprocal. So we have 7.58 k ohms. Now, I don't know if you're going to have time on the test. It's according to how fast you can work your calculator. If you work your calculator fairly rapidly, I would advise you to do this twice. Do each of them twice, if you can. But what I would do, if you're fairly slow at it, I would do them once, and then when you get done with everything, then I would go back and do them again. But be careful, don't change your right answer. Okay, we're going to clear the calculator. We're going to do the same thing we did before. Notice here that we could use the product over the sum because there's only 2 resistors. But you and I know how easy it is to use this calculator. So what we're going to do, we're going to put in the 8, can you see that? Yeah, you can. We're going to put in the 8.2k, and we're going to parallel that with 100k. So here's what we do. We put in the 8.2 double E, what? Double E 3. Now I have 8.2 double E 3, which is 8.2k, and it's in parallel with 100k, so I have to use my formula, my reciprocal formula, and take the reciprocal of that. I'm using a reciprocal formula. Okay, plus 100 k ohm resistor, that's 100 double E 3 reciprocal equals, then reciprocal again, 7.5 k ohms, and that's what we got before. See, by checking it twice, unless you make the same mistake twice, we're pretty sure that you're going to get it right. Now let's move right along. I'm not going to do every one of these. I know that most of you know how to do them. I'm doing different kinds of problems. I just wanted you to see how these work. Okay, number 9. Let's do number 9. Okay, number 9 says 12,000 ohms in parallel with 9,000 ohms. Now, how are we going to do that one? What I would do first, I would go in and change this to k ohms. So we have a 12 k ohm resistor in parallel with a 9 k ohm resistor. And that equals, let's do it on the calculator. I'm going to rearrange here a little bit. Alright, we need to clear the last one out, remember. Keep that calculator clear after each problem. Now, we look at the problem and we say we have a 12 k ohm resistor. We're doing this using a reciprocal formula. We punch in a 12, don't we? Okay, the next thing we do is double E, and we're doing K, so it's a 3. So there I have 12 times 10 to the third, which is indeed 12K. Now, it's in parallel with a 9K. So I hit the plus, I hit the 9, double E3 for 9K. That's what we have in the window. Then the reciprocal, and no plus this time, it equals that. Did we do it wrong? I don't know if we've reciprocaled too many times here. Let's try it one more time. Okay, 1, that's 12, double E3, reciprocal, plus 9, double E3, reciprocal, equals that, 5.14 times 10 to the third. I'm going to write that down, and then I'm going to do it again. 5.14 times 10 to the third, and what that equals is 5.14 k ohms. So let's do it again, just for grins. Okay, just to make sure we're right, we put in a 12, and then we put in double E, we put in a 3, we got 12 times 10 to the third, and then we reciprocal that, and then plus 9 double E3 reciprocal equals that. Again, we know that it's not going to be a negative exponent, so we know we got to hit the reciprocal again, and we get 5.14 times 10 to the third. See how that works out, how easy that works out if you use your calculator, if you know how to use your calculator. For those who are not in the class, I would advise that you get this TI-30XA. You can do almost any of the technician type problems that you want to do with this. You can do AC, you can do DC, you can work on a number of different kinds of problems. And it's simple. That's the great thing about this. It's simple, it's durable. I've had this one about 5 years. I'm still using the same battery. Now there is another one just like this that has a solar cell up here. And that's a handy thing if you're a student, because if in fact your battery goes out during a test, that wouldn't be a good thing. So if I were a student and only spent $8.95 for this calculator, I would buy 2. I think I like this one. The batteries lasted really well. Okay, with that said, let me try to pick out another one that see if it would give you any difficulty. Now here's one that's written a little different. I'm going to do number 10. I'm going to do number 10 here. Okay, number 10 says 10 times 10 to the third ohms, and also that's in parallel with a 15 k ohm resistor. Okay, that's sort of crowded there, but I didn't see that I was going to run into it. Okay, let's do this. What I would do when I first looked at this problem, I would say that is actually 10 k ohms is what I would do. I would say that's a 10 k ohm resistor, because it is. And then I would say that's in parallel with a 15 k ohm resistor, which it is. And I would say that that equals, you could work it 2 ways, couldn't you? You could use the product over the sum, which some of you like, but quite frankly, that's only good for a couple of resistors. I just soon do them all the same way and only have one formula. Okay, so we're going to use this formula over here. We're going to use a reciprocal formula, and we're going to say that we put in a 10 for 10 k ohms, and then we hit double E to put in the k. I have 10 times 10 to the third, which is 10k, and then I'm going to say reciprocal. Remember, don't forget the reciprocal, because you've got to take a reciprocal of that. Okay, plus 15 double E3 reciprocal equals that. And then I need to take the reciprocal of the whole thing. I've done the reciprocals here, then the reciprocal of the whole thing equals 6 k ohms. Let's see if that's what it turns out to be. Okay, let's just go ahead and work that using the product over the sum. We could have just done it again, but I just want you to see that both these formulas turn out to be the same. product over the sum is R1, R2, divided by the sum of R1 plus R2, and that equals, what do we have here? We have 10 double E. Can you see the calculator? Let's move it over a little bit. Okay, we have 10 double E3 times, this time times 15 double E3 equals that, divided by R1 plus R2. How much is R1 and plus R2? 25K. Double E3 equals 6K ohms. See, it turned out to be exactly the same. But again, why I like the reciprocal formula, it'll solve any of these parallel problems with any number of resistors. This product, though, over some, we can only use on 2 resistors. You know, why remember that another one that you don't need to? I do like the one here, though, where they're all the same, especially if you have a long number of resistors. If you only have 2 or 3, I'd use a reciprocal. But if you have more than, say, 3, it doesn't hurt to use this formula here, where RT is equal to one of the resistor sizes divided by the number of resistors. Okay, is that enough? Let me look and see if there's anything else that might give you a problem. I'm going to put this one aside for now, and I'm going to get another sheet of paper, which I'm doing now. Okay, so let's look down the list. The students have the list just like I do. Now let's see what else looks like it might give you a problem. Actually, I don't see any more that will give you a problem. Let me look. Yeah, there might be one here. The one using meg. We haven't talked too much about that. So it's important that you be able to work that one too. It's in our particular chapter, that hasn't been a big problem because we haven't had many resistors that were meg. But there's a few. So let's learn to work those also. Let me see which one I want to work. Well, I don't see one that's very hard. I was trying to find one that might give you a problem. They all look simple and straightforward. Let me make up one in my head that's not one that we have here. Oh, here's one. Let's do number 17. Okay, number 17 on your list, and that's a 100 K ohm resistor, and that's in parallel with a 2 meg resistor. Now, notice here that this is a capital M. If that had been milliamps, it would have been a small m. But it's not milliamps, this is meg. And what do you think meg stands for? 10 to the 6, doesn't it? For million. 10 to the 6. Metric symbol for million here. And here's what we're going to write down. I'm going to, we'll do this 2 ways. Okay, we can start off by saying this, that we have a 100 K ohm resistor, and it's in parallel with what? 2000 K resistor. Does that make sense? Okay. Okay, here's how we figured that out. Because 2 million is this. Okay, that's the 2 million. And what we can do is make that into K. And the way we do that, of course, is we want to group this into 3. You have 2,000, what? 2,000 K ohms. But let's work with that on the calculator. It's not going to be a problem on the calculator. Only thing we're going to have to do on the calculator is remember that this is the power of 6, and this is the power of 3. I hope you can see that. I think you can. Yeah, I'll get my hand out of the way. So on the calculator, this k is going to be a 3, and this m is going to be a 6. So you don't need to remember all the rest of that stuff. I just wanted you to understand what they're doing. It's a good thing to know what you're doing, but it's a good thing to have the right answer too. And your calculator will help you get the right answer. I'm a firm believer in them. I know when I was younger, I had to do these longhand. They were tedious, to say the least. And then something came out that's been out for a few thousand years, is a slide rule. And finally I was introduced to one. And let me say this, I still think the slide rule is a good instrument. And I wouldn't mind to see some of the students using that. But of course you better stick with this. Your grades are important. You better stick with this calculator, because quite frankly it's easier to use and it will give you the right answer. I want you to know there's other ways. And the slide rule was used to put men on the moon. That was back in von Braun's days, and many of the missile scientists, rocket scientists, that's what they used. Of course they used other things too, but the slide rule was the symbol of an engineer. Okay, now let's work this problem. Real simple to do. Don't get confused by any amount of zeros or anything else you have. It's a simple mechanical thing to do this. I look at this 10K, so I put, I'm sorry, 100K, so I'll put 100 in there, and then what do? I got a double E. Since it's K, I put in a 3, don't I? Now what's next? I'm using reciprocal formula, so what do we have to do? We have to take the reciprocal. And then what do? We plus this 2 meg. And the 2 meg is simply this, 2 double E 6. Okay? And then reciprocal equals, then reciprocal again. Did I hit the reciprocal? Yeah. 3.52 is what we come up with. No, I'm sorry, 9.52 times 10 to the 4th. Okay, let's look at that. Now, remember we discussed this before, how to make this into K. We've got 9.52 times 10 to the 4th, and we want to make that into K, so we need to get rid of one of these and make this a 10 to the 3rd. And of course the way we do that, we move the decimal point here to the right. So 95.2 what? 95.2 K ohms. Let's do that one more time. Make sure we're doing this right. I'm going to rewrite it. And this is number 17. I have 100 K ohms in parallel with a 2 meg ohm. And what is that going to equal? Remember, we could have done that with the product over the sum. Just as easy. But this is my preferred method. Use on a test what you want to use, just so you get the right answer. But if I were you, I would at least try to document your formula and so forth. It's not necessary. If you get the right answer on the test, it's the right answer. Okay, let's do this. We'll do this fairly rapidly and hopefully come up with the same answer. Let me position this so that you can see it. Okay, I'm sure you can see that now, or most of it. Okay, I'm going to clear the calculator. Always clear the calculator. I put in 100 for the 100K here. Double E, and for the K, I'm going to put in a 3. And that's what I have up here now. I have what? I don't have the right number. Okay, I put in a 10 instead of 100. 100, double E, 3. And then what do? Reciprocal. And then what do? Plus 2 meg, which is 2, double E what? 6. reciprocal equals, then we take the reciprocal again. And I come up with 9.52 times 10 to the fourth. And that's exactly what we got before. And here's what we did. We had 9.52 times 10 to the fourth. I know some of you have had a problem moving this before, but now you won't. We want to make this at a 3 if we can. So now that's 10 to the third, because we're going to move the decimal point over one place. Remember, we call this a caret. This is where your new decimal point is. So you have 95.2 K ohms. Now, I hope I got all these right. I hope that you will, if I made a mistake, that you will email me right away so no one gets the wrong idea of how to work these problems. I've enjoyed doing these, and if you will, go ahead and let me know you got these, and let me know if you understand how to do them. That's the most important part. I'm going to try to review some more things today, and if I don't get to them today, I'll get to them in the morning, and that'll give you plenty of time to study them on the test. We could cover a few things right now. Do you want to do that? I think we probably should. I hesitate to do that because I was not prepared for it. But give me a couple of minutes. That'll give you time to think, and I'll grab the textbook. That's no good. Okay, I'm sorry for the delay. I was going to end this video. I don't know how long I've been going on with this, but hopefully you two will put it all on there. Now, what we're going to talk about now is some items that are in the textbook. And let me grab these and get organized real fast. Okay, are you ready to go? These are just some items that to summarize the chapter 5. The most popular application of parallel circuit in electronics is used as a current divider. In a parallel circuit, the total power is calculated by P1 plus P2 plus P3, etc. So you add the powers of each resistor when they're in parallel. In a parallel circuit, the largest amount of power is dissipated by the smallest resistor. We discussed that earlier. We discussed it in lab. Okay. A short is like a wire or a ring or whatever goes across the circuit. A short in one branch of a parallel circuit results in an increase in current flow. Let's do some true and false. Okay, Kirchhoff's current law states that the sum of the currents into a junction must equal the sum of the currents out of a junction. Is that true or false? Well, that's true. The total resistance of 4 resistors in parallel is always less than the smallest resistor. We talked about that today, didn't we? And the answer is it's true, because we're always going to have, when we combine parallel circuits together, the resistors, it's all the resistance of the total is going to be less than the smallest resistor. Now, here's something, don't let it throw you. If you see a problem like this, if it gives you two different currents, and it gives you the total of the two different currents, it will ask you, is that true or false, the amount they get. Now, in some of those it's going to be true, but in some of them it's going to be false. So what I recommend that you do is go ahead and work the problem. For example, if you have two currents, that's a 2 amp in R1, and you have a 3 amp in R2, they may give you a figure that doesn't say 5. And if it doesn't say 5, then it's wrong, because that's how much R1 and R2 total would be, is 5 amps. Okay. The total power dissipated by a parallel circuit can be found by adding the individual powers. Well, yes, that's true, because PT, power the total power in a parallel circuit, is equal to P1 plus P2 plus P3, etc. If one branch of a parallel circuit shorts, what does that mean? It shorts. That's where it's shorted out. Now, if you short out one branch of a parallel circuit, you're going to short out the entire circuit. So what's going to happen to current? Current is going to increase, isn't it? Now, listen to this carefully. It's always in the wording. If a parallel circuit can be easily identified because of only one end of each component is connected to the other. Now, that would be a series circuit, wouldn't it? So, of course, that would be a false question. Okay. Now, we talked about this before. You cannot accurately troubleshoot a parallel circuit with a voltmeter. And the reason is because the voltage is going to be the same across all the resistors, regardless if the resistor is open, the voltage across it is still going to be the same, isn't it? And total power for parallel circuit can be determined by the same methods as a series circuit. Well, that part's true. It's something that's unusual or the same in a parallel and series is the power, because the resistors are going to dissipate the same power regardless of what kind of circuit they're in. So if you saw a question, total power for a parallel circuit can be determined by the same method as a series circuit, of course that's true. Now, if a 3 resistor parallel circuit, R1, R2, and R3, we're not going to do that one, I deleted that. If 12 1.5 meg resistors are connected in parallel across a 50 volt, how much is RT? Now, it's something important you looked at. You're going to get confused when you see that 50 volts. It's not necessary to know that 50 volts, is it? All we have to do is go ahead and get RT by several methods. We can use what? We can use the size of the resistor divided by the number of resistors. That's one way. And the other one is the reciprocal formula. So don't worry about those particular types of problems where it's asking for RT, unless one of the RT is not one of the resistors are not known. You don't need to know what the voltage across them are. If one resistor opens in a parallel circuit, what's going to happen to the current? The total resistance will what? Now we talked about this the last day of class. Remember, in that back on the bench there, we opened up some resistors. What happened? The total resistance increased, didn't it? Parallel circuit, the total resistance increased, and the total current did what? Decreased. So when you open up a part of a parallel circuit, the resistance is going to increase and the current is going to decrease. Now this is a real easy one too. If you had 3 22 k ohm resistors are connected in parallel across a 10 volt source, power PT equals what? Now in this case you do need to know the voltage, don't you? Because we're going to figure power. And power in this case equals what? I'm listening. But you're not answering. Okay. Know your formulas. Go ahead and figure out what power equals when you're given R and you're given E. You need to write that down and maybe play this a couple of times to understand what I'm talking about. Okay, let's do this one again. If one resistor shorts in a parallel circuit, what's going to happen to the total current? It's going to increase. It's going to increase a lot. It's going to increase so much that you either blow a fuse, or if the fuse is, if you don't have a fuse, you're going to blow a component. Now if you have 4 100-watt lamps are connected in parallel across a 120-volt source, what is the total current? Well, you have to figure out what I is. If you're given P, which is the 100 watts, and you're given E or V, which is 120 volts, then it's easy to figure out current. You know the formula, you're going to have that formula on your formula sheet. If you measure a lower than normal total current in a parallel circuit, what does that tell you? Now let's think. Think back what I just said. If you remove a resistor, the current is going to decrease. So if you remove a resistor, and it would be removed for all intents and purposes if the resistor opened up. Open means that there's no current going through it. Well, what's going to happen in that case is that a resistor is open if go ahead, if a lower than normal total current is in parallel. Okay. A formula that applies to a two-branch parallel circuit is what? How about RT equals R1 plus R2? No, that's not right, is it? How about VT equals VR plus VR2? That's not right. How about IT equals IR1 plus IR2? Yes, that's right. Because the currents are additive in a two-branch, aren't they? They come into the node. You have a certain current. Let's say you have 6 amps, and the current going out is going to be 6 amps. Okay, the current through any branch of a parallel circuit is inversely proportional to the branch resistance. Now stop and think what that actually means. The current through any branch of a parallel circuit is inversely proportional to the branch resistance. Does that make sense to you? I equals E divided by R. If R goes up, what happens to I? If R goes up, I equals E over R. R goes up. What's going to happen with I? It's going to go down, isn't it? So they're inversely proportional is what I'm getting at. If you want to measure a load voltage with a DVM, and that's a digital voltmeter, connect the meter in parallel. Now, don't you remember how you measured all those voltages in those labs? The voltages across the resistor. You're going to be in parallel with your meter, aren't you? So using the DVM, which is a digital voltmeter, you're going to be in parallel across the resistor. And what about a current meter? A current meter will go in series, won't it? Okay. If you had a two-branch parallel circuit containing R1 and R2, and you knew IT, how would you find the voltage? You know R, you know I. How would you find the voltage? Well, that's real simple, isn't it? E equals I times R, and conversely, I mean the same, V equals I times R, doesn't it? E and V are used interchangeably in a lot of places. Now, industry is trying to get away from the E, but again, it's in both of our lab manuals, so